Bismillahirrahmanirrahim. In this video we will discuss the convolution of two signals x of t and h of t. Why we will consider that x of t and h of t are the two rectangular functions. You know that the convolution is represented by the integration of x of tau into h of t minus tau with respect to tau from minus infinity to infinity when we are convolving two signals x of t and h of t. You can also write down this convolution integral like that this is h of t into x of t minus tau with respect to tau from minus infinity to infinity. In either way you can work out the convolution, it doesn't matter. I will consider this x of tau into h of t minus tau to find out the convolution of two signals x of t and h of t. Basically what you are going to do, you are going to take this signal h of t and then you are going to work out what is h of tau, means you are simply replacing time with tau, and then you are going to find out h of minus tau and then you are going to shift it by the time t so that it is represented as h of t minus tau. So these are the steps to find out this one h of t minus tau when h of t is given, and in the x you are just replacing time with the tau. So now let's do it step by step and we try to understand the convolution of two rectangular functions. Okay, so our first rectangular function that has been taken over here is from -1 to +1, that is 1 in this interval, otherwise it is 0, and this is x of t. So first of all we are going to represent it as x of tau, means we are going to simply replace this variable t with the tau, otherwise it is exactly same as shown above, only the variable along the x-axis is changed from time t to tau. So our signal x of tau is represented like that. So our first signal is ready according to this expression that we have developed, x of tau from x of t. Okay, now let's work out for h of t minus tau from h of t. So let's suppose that our second rectangular function is from -2 to 2 equal to 1, otherwise it's 0. It's a rectangular function centered at 0 starting from -2 till +2. Okay, so our first step will be to replace this t with the tau, and by replacing this t with tau there will be no change except that x-axis will be represented by tau, rest of the signal is going to remain same. What is our next step? In the next step we are going to represent this h of tau as h of minus tau. So that basically means that flipping the signal across the y-axis. So if you flip it, and as you can see over here, our signal is centered at 0. So when you will flip it across the y-axis, this is going to be over here and this is going to be over here. So there will be no change, that will remain same. So our signal limits will be from -2 to 2 when it will be flipped across the y-axis. So there will be no change as it is centered at tau is equal to 0. If it would have been displaced, then of course this point and the starting point and the ending point will be changed when you will be flipping. Okay, so now after working out this h of minus tau, now we are going to shift it by the time t because we want to work out this expression. Okay, so now how to work out that one? An easiest way to do is to add time with all of these ones, because if you add t in this one, t plus 2, this point will be shifted, this will become t plus 0, this is going to become t minus 2, and that you can see over here t minus 2, t plus 0 and t plus 2. So this is h of t minus tau. So in order to shift this signal by the time t, what you are going to do, you are going to add that time t with all of these points So it's an easiest way to represent your signal h of t minus tau, that is the shifted version of this h of minus tau with the time t. You can also write it like that, that this is equal to h of minus tau plus t. So you have basically shifted it towards the left hand side by adding the t with all the points. So we have prepared our signal h of t and we are going to represent like that now at h of t minus tau by shifting it by time t, and the other signal that we have already worked, that is x of tau, that is from a minus 1 to 1, that is equal to 1, otherwise it's 0 because it's a rectangular function. So now we have prepared two signals and those are shown over here. The center point of this one is now t, right, and now we will be convolving them. So basically what's the convolution is, as we have seen above, convolution x of t with h of t, that is the area from minus infinity to infinity, that is covered by the product x of tau and h of t minus tau with respect to tau. So basically what's the integration is? Integration is the area under the curve, and which curve? That is defined by the product of x of tau and h of t minus tau. So by taking their product, we will see that as the time will be progressing, what will be the area accumulated by that time, that will define the till that point. And if you want to convolve whole wave signals, then from minus infinity to infinity, whatsoever is the area covered by the product of these two, that will be equal to the convolution. So as the time will be progressing, so when the overlap of the two signals will start, so area accumulated will be changing. So we want to work out that one basically, so that you can better understand. If I take let's suppose this signal, that is our first signal, and now if it starts moving towards the next, let's suppose x of tau, so is there any area overlap? No. Up to when t plus 2 is less than minus 1, there is no area overlap, so no convolution result over here. Once this t plus 2 becomes equal to minus 1, as you can see over here, so there is no overlap, but the overlap is now going to start. Now if I move it onward, let's suppose over here t plus 2 is greater than minus 1, here you can see a small overlap. As this t plus 2 will be increasing, so more and more area overlap. So now t plus 2 has become equal to 0, you can see this highlighted overlap, and so on. So when the t plus 2 will become equal to 1, the area overlap will be increasing up to this point. So starting from t plus 2 equal to minus 1, as the t plus 2 will be increasing, you can see area overlap is increasing, and that area is basically representing the convolution result of x of t and h of t minus tau, or h of t. So now up to this point, when the t plus 2 is going to become equal to 1, your area was increasing. But after that, if you move onward, you can see that there is the area overlap, but it is not changing, it has become constant, and this will remain constant up to this point when the t minus 2 will become equal to minus 1, right, over here if I move it above. So when the t minus 2 will become equal to minus 1, and after that, if I increase t minus 2 onward, or if I increase t, because if I will be increasing t minus 2 will be increasing, so area overlap will start decreasing. And as the t will be increasing such that t plus 2 becomes equal to plus 1, area overlap will become minimum, and as the t will be increasing further, t minus 2 will be greater than 1, and now there is no area overlap. So basically what we do in the convolution, we change the time, and one signal is basically moved through the other, that you can see over here. So before that, area overlap is 0, and once the time t is increasing such that t plus 2 is greater than minus 1, area overlap will be increasing. First of all, we will consider that t plus 2 is less than minus 1, so area overlap is 0, and then t plus 2 becomes equal to minus 1. So when it will move onward, area overlap will start. So our second case integration limits will be from minus 1 to t plus 2. As the time will be increasing, the area will be increasing. So from -1 to t plus 2 we'll be integrating, and we will be getting the area under the product of x of tau and h of t minus tau. And now you can see that t plus 2 has become equal to 1. So if it becomes greater than that, there is no change in the area, constant overlap. And once the t plus 2 becomes equal to 1, at that time what is t? T is equal to, just observe, t is equal to -1. So when t is equal to -1, the constant overlap starts, and when the t is greater than now -1, this area is constant, and up to which point it will remain constant? Till this t becomes equal to 1. Up to this point it is constant, and once the t becomes greater than 1, this is going to change again. So we can define in terms of t that starting from -1 to +1, area overlap is constant. And we can also define it in the other ways like that. Let's suppose we can say when t plus 2 that is greater than 1, t plus 2 is greater than 1, there will be a constant area overlap, and this will remain constant till t minus 2 is less than -1, considering the left hand side edge. T minus 2 is less than -1. Once t minus 2 becomes equal to -1, constant area will be ended, and if t minus 2 is greater than -1, now area overlap will be decreasing. So we will take the limit from t is equal to -1 to 1 to work out that constant area. And then when this signal will be moving away from that one, when t minus 2 is greater than -1, so now area overlap will be decreasing. So our limits of integration to work out the area will be from -1 to t minus 2. And as this t minus 2 will be moving onward till the point, this one, when the t minus 2 becomes equal to 1, area overlap will be there, and after that there will be no area overlap. And that when the t minus 2 is equal to -1, and till the point when t minus 2 is equal to 1, the area overlap is decreasing. So in this way we will define the limits of the integration to work out the area under the product of x of t and h of t minus tau, and we will work out the convolution expression. Okay, so considering the first case when there is no overlap and this signal is going to move onwards, so when this till the point this t plus 2 is less than -1, there is no overlap, so area under the product of x of tau and h of t minus tau is 0, right? Now this we are going to call it the case 1 when there is no overlap. Okay, now once the overlap starts, that you can see over here, when the t plus 2 is now greater than -1, as this will be moving onward, it means this t will be increasing. This t minus 2 is basically moving in this direction, all of that signal. So you can see an area overlap, and this will be increasing as this signal will be moving towards the right. So how to set up the limits of integration from -1? So this is the lower limit of integration of the product of x of tau and h of t minus tau. This is the product. So from -1 till the point t plus 2, and that will be defined by the time, at what time stamp you are working the area. So from -1 to t plus 2, you will be evaluating the integration of the product of x of t into h of t minus tau, and that is from -1 to t plus 2 of that signal. Why it is 1? Because this is 1 and this is 1, so their product is 1. So that will be, their integration will be tau, and limits will be from -1 to t plus 2, and that will be equal to t plus 3. So as this time t will be increasing, so you can work out the area accumulated by that time by the overlap of this h of t minus tau and x of tau. Okay, so our lower limit is -1 and the upper limit is t plus 2, and as it will be continued till this point. And what is this point? Up to which point it will be increasing, that is t plus 2 becomes equal to 1, or you can say up to the point when t plus 2 is less than 1. So it means when t is less than equal to -1. So this is the limit over t from -3 to -1, because at this point over here you can see when the t plus 2 is greater than -1. So what that means, when the t is greater than -3, right? So from this point till this one, when this overlaps is up to this point, your area will be increasing. So t plus 2 is less than minus 1. So from here we can say t is less than minus 1. So one limit is this and the other limit is this. So these are the limits of the integration to work out the area under the product of x of tau and h of t minus tau, and that is given by this expression. Okay, now let's look at the case number 3. In case number 3, we are going to consider that this t plus 2 has become greater than plus 1. So the signal h of t minus tau is moving through x of tau, but as the width of h of t minus tau is more than x of tau, so that's why the constant overlap of the area is there. So the limits can be worked out now. When the t plus 2 is greater than 1, it means t is greater than minus 1. So when this t is greater than minus 1, the constant area overlap will be there, and up to which point it will be there, till this t minus 2 is less than minus 1, right? So that gives us that t is less than 1. So when the t is between minus 1 and the 1, we have the overlap of the two signals, and the area is constant, area overlap, right? So this is our third case. And how to work it out mathematically, that x of tau into h of t minus tau, their product, and the integration will be from minus 1 to 1, because our overlap is over here in this interval from minus 1 to 1, and the area overlap in this interval, that is constant when this h of t minus tau is moving onward with the update of the time. Okay, so that is equal to the constant area overlap. Okay, now let's consider the case when this t minus 2 enters over here. It becomes greater than minus 1, and that is shown over here. T minus 2, when it is greater than minus 1, so now the overlap of the area is decreasing, because the first signal is from here. If I change the color for that one, the first signal is over here and the second signal is now crossing that one. So area overlap is reducing as this h of t minus tau is moving onward. So now we want to work out the limits. So how to work out those? When t minus 2 is greater than minus 1, it means when t is greater than 1, means when this t is greater than 1, so the area overlap will start decreasing, and this will be decreasing till this t minus 2 is less than 1. So that is the second limit, upper limit. So this says that t is less than or equal to 3. So when the time will be varying from 1 to 3, there will be a decrease in the area overlap of these two signals, and our integration limits are from t minus 2 till this point 1, because during this there is the area decrease or the change in the area overlap. So from t minus 2 to 1, x of tau into h of t minus tau, if you work out that one, so 3 minus t, this equation will be giving us that how area overlap is going to change with the change of the time t. Okay, now if we combine all of these equations together, those we have worked out, when the time was less than minus 3, there was no overlap, area overlap was 0. When the time was between minus 3 and minus 1, the h of t minus tau was moving through x of tau, so our area overlap was increasing, and it is given mathematically by this equation, that t plus 3. If we plug in the time, up to that time we can work out how much area has been accumulated. So as the time will be increasing, so area covered by the overlap of those two will be increasing, and that will be increasing up to when the time becomes equal to minus 1. And once the time is greater than minus 1 and it is between it is less than 1, there is the constant overlap, and that is shown over here in this region, that from time t is equal to minus 1 to t equal to plus 1, there is the constant overlap. And once the time becomes greater than 1 and it is between 3, so that you can see over here, it is representing this one, the area overlap will be decreasing. So you can see as the time will be moving onwards, so our area that is covered by the overlap of the two signals, that will be decreasing, and once the time becomes equal to 3, the area overlap ends, and once that h of t minus tau is moving onward, such that the t is greater than 3, so then there will be no overlap, and that you can see that area becomes 0. So when you are going to convolve to rectangular function, the result is the trapezoidal function, and that is shown in this diagram, right? So what you can conclude from here, what is the convolution? Convolution is basically the area under the product x of t and h of t minus tau. So this integration represents that area, and that is the convolution of x of t with h of t. So basically how that overlap area is changing, and up to a certain point how much that area has accumulated, that represents the convolution, right? So if I conclude this video, we have discussed the convolution of two rectangular function, and the convolution is the area where that is covered by up to time t when one signal is moving through the other signal, and we have discussed that how we can represent it mathematically. So when the area overlap will be increasing, the x of t h of t convolution, that is the area under the product of those will be increasing, and once the area becomes constant, and then it will start decreasing, and finally is going to become 0. So we have graphically seen that how we can work, what is the meaning of the convolution, and when we convolve to rectangular function, what will be the result of that one, and that is the trapezoidal. So x of t and the h of t can be any two signals. We have considered rectangular function over here in this video. In the next upcoming videos related to convolution, I will take different functions, and we will see that how the convolution is worked out for those ones. So hopefully you would have understood the basic concept of the convolution. And that's all from this video. Thank you very much.